This one's like half the class. I don't know what's up. I guess it's just maybe it's because it's 3:30. That's I'll just start talking. I actually have I'm going to skip a lecture with you guys. We kind of stopped, we were talking about orbitals last class, and I said that we're going to follow up talking about orbitals today. And I think I might go back on Monday and talk about orbitals again. In fact, I will talk about them on Monday. We're just going to swap the order. Okay, so I'm going to do Monday's lecture today and today's lecture on Monday. Okay. And the reason why is because I want to do this discussion, this lecture today, so you guys can have the weekend to work on the homework because you kind of need the material. We don't really study orbitals too much on the homework. Right? We'll look at orbitals more on the following homework 5 when we're talking about molecules and different types of atoms. But I want to talk about energy levels today because that's more relevant to our conversation in problem 1 and problem 2 in particular, and problem 3. Right? Just generally a more relevant discussion for problem set 4. If you didn't see it, I pushed homework 4 back to Wednesday. So it'll be due on Wednesday instead of Sunday, which is the day I'll bring up homework 5 as well. So plenty of time, getting a chance to go talk to Kayla and Allison, and so on. Okay, up on the board here, I have a historical document, figure, if you will, made by Joseph Fraunhofer, German astronomer, 1814. Fraunhofer is, in some sense of the word, the world's first historical spectroscopist. He was the first person to really start thinking about what we call spectral lines. And he was the first person to identify these absorptions that we now kind of treat for granted in chemistry. But in the 1800s, we were barely at a point where we could appreciate that things can emit light. We were finally understanding light. And what Fraunhofer realized is that from certain sources of light that he was studying, that there were gaps in the emission. So what I have here on the picture is a recreation from Fraunhofer's 1814 paper on the spectrum of the sun. So Fraunhofer was an astronomer. He used William Herschel's spectrographs. He was a British astronomer. He developed what's called a spectrograph, which is basically a fancy prism that took light in from a telescope and then split the components across the colors, right? What we call a diffraction grate, a modern version of a prism. And so Fraunhofer used Herschel's diffraction grating technology to study the spectrum of the sun. And what we have here on this is his plot, if you will, his graph from 1814. And what we have here are two different pictures of the sun's emission. The smooth curve on the top is what we call the black body emission spectrum. And this is just kind of like if you take a colorimeter and you measured the intensity of each color coming from the sun and just kind of marked it in a rough way, and you made a smooth curve, this is what it would kind of look like. So I'll draw exactly, he actually has the colors in green, or the colors are here in German on the bottom. This is red, orange, green, indigo, and violet. And he shows that the peak of the emission of the sun is in the green, which is 100% correct. The sun emits largely green light. It emits a broadband spectrum of light, halo spectrum of light, but it peaks in the green. We don't see that because we see all the colors. When we have in an additive color scheme, all the colors looks white. And because of scattering from the atmosphere, it can sometimes have a bluish or a reddish tinge. We don't really see the green. But the majority of the maximum emission is green. And then what he did was say, okay, this is what the rough emission looks like. And then he used that diffraction grating, that spectrograph, to split the light up as finely as possible. It's something like increase the resolution of his spectrum. And so on the bottom is a recreation of the spectrograph that he recorded of the sun. And what he observes is that there are large swaths of missing light wavelengths. So the white areas in the bottom plot are emissive wavelengths, and the blacks are places where the light is missing. So of course now we would call these absorptions, right? This is an absorption spectrum. And interestingly, you'll see that he notes on the labels, you see in between the two plots, there's like A, B, C, D, E, F. And he particularly names the particularly strong absorptions, A, B, C, D, E, F. So here's the A, right? There's a line here by itself. There's a line here by itself, B, a line here by itself, D, and so on and so forth. And so Fraunhofer doesn't know anything about anything. He just sees this. He's got no concept of what's causing this. Zero concept. He just knows that there's things missing. And he says, okay, well, I'm just going to label them A, B, C, D. Interestingly enough, we continue in kind of common parlance in science, we continue to use Fraunhofer's notation. The A line is what we call the Walmart alpha line in hydrogen. It's the red emission of hydrogen. The D line is that characteristic yellow color that sodium lights on the highway give you. You ever see those orangish yellow lights on the highway at night? That's a sodium discharge light, the sodium light. And that's the D wavelength. And we call them the sodium D lines after Fraunhofer. So Fraunhofer identified all of these absorption lines, but he's got no physical or scientific chemical concept of what's doing this. No concept, right? He just knows that they're missing. Not surprisingly, that became a huge revolution or the surprise in physics, in astronomy and chemistry, that there are missing wavelengths from things that otherwise emit continuously. So through the 1800s and into the 1900s, a big part of chemistry, very, very large part of chemistry, if you weren't doing reactions and figuring out what atoms are and doing chemical formulas, molecular formulas and stuff, that kind of traditional wet lab chemistry, you were doing spectroscopy. Because this is one of the biggest unsolved problems at the time, right? Why is there missing light? And it wasn't until people started discovering, right, at this point, no one knows what an electron is, no one knows what a proton is. Hydrogen was identified. People knew what hydrogen was from Antoine Lavoisier in the 1700s. We knew that there were atoms, oxygen, hydrogen. That was all done within about 100 years of this. So some basic general chemistry was available, but we didn't have any concept of the optical properties of atoms. No concept that hydrogen will emit or absorb particular wavelengths. This is our first indication that something is up. So, of course, what Fraunhofer is interested in is, of course, what is the sun made up of? And so he's probably indicating that whatever is causing this must be the carriers of the mass of the sun. They still didn't even know it's hydrogen and helium in the sun, right? I mean, at the point, this is how far back we are in scientific development. They didn't even know the sun was made out of hydrogen. So this was a constant kind of unsolved problem through the 1800s. It wasn't until the 1900s when our ability to start doing spectroscopy in the lab becomes possible, where we can create light sources in the lab and analyze their spectra using a lab chemical sample instead of using the sun. It's a really easy light source. It's much harder to make your own light source in the lab. I mean, back then we only had candles anyway, right? So how the hell are you going to do spectroscopy with a candle? That's a terrible way to do spectroscopy. So light started to become available, and so we could finally start doing spectroscopy in the lab. And the advantage of doing it in the lab is that we don't have a complex mixture of stuff. We can grab hydrogen by itself and isolate it and study hydrogen by itself, or helium, or neon, or oxygen, right? So in the 1900s, show you another beautiful picture. Comes from, this is 1906. A man named Teddy Lyman. He was at Harvard. He was a Harvard astronomer. Publishes UV spectrum of hydrogen. Okay, and I'm going to show you a recreation of what he has. I can't find the original plot that Lyman published. I'll have to dig for it. But what he sees in the infrared or in the UV is something that looks a bit like this. So this is an emission spectrum. All right, and Lyman, this is in wavelength. Let's just, an angstrom, that's kind of an old-fashioned unit for wavelengths. But we can convert that into nanometers. This is 125 nanometers. This is 90 nanometers. Right, and of course, wavelength goes in this direction, and energy goes in this direction, right? So what Lyman notices is that in pure hydrogen, he sees those discrete, separate absorptions or emissions, however you want to think about it. Doesn't really matter. But he sees this pattern, and he notices there's a pattern, right? That hydrogen forms this interesting pattern. These lines seem like they all are converging to some limit. I've written that up there. And he finds that no matter what he does with the sample, right, he gets the same result each time. You can see that this is approaching some limit. Oops, sorry. And he labels, just like Fraunhofer, he labels the lines alpha, beta, gamma, delta, epsilon. So this Lyman alpha line is an interesting one. It's by itself, right? This is kind of an interesting line. It's completely by itself. All the other ones are kind of clumped up together, as you see, and they get increasingly more clumped up. This one out by itself is like a nice little fingerprint line. Call that the Lyman alpha line at 121.6. And we use Lyman alpha all the time in spectroscopy. And actually in astronomy, it's anytime you have hydrogen atoms, they glow bright in the Lyman alpha band in the UV. So we use Lyman alpha to study hydrogen everywhere. I will try to find a nice picture of it. Here's a nice picture, a very dramatic picture of what's called a Lyman alpha blob. This is a dying star that is maybe being consumed by something. Maybe it's starting to fall apart, and you have these streaks of hydrogen, these jets of hydrogen sending out highly ionized H atoms. And so we can study these things by looking at the Lyman alpha line. So all of this is done. This is in false color, but the wavelength is set to 121.6 nanometers, right? So really, really nice way to study hydrogen. Hydrogen atoms are abundant in places that are very violent, hot, because you got to be pretty hot to have hydrogen atoms. Otherwise, you have H2, right? So you kind of have to have kind of extreme environments to see H. So this is what we call Lyman alpha astronomy. Okay. It's a really nice way to measure H. But Lyman doesn't have any appreciation for any of this. In fact, in 1906, they didn't even know that there were galaxies at this point. Okay, so astronomy is so far behind at this point. Everyone thought that when they look up and they see galaxies in the sky, they just think that they're things that are in our neighborhood, not that they're completely separate from the Milky Way. It's kind of ironic. I don't know if you guys know this. The person who, in some sense, proves and convinces the world that not only are we alone, but the majority of the things we see in the sky are way farther away than we know. Was a priest at the Vatican. The head of the Vatican Observatory was one of the people that proved that galaxies are in fact galaxies. Regardless, though, so Lyman sees this pattern here. It's very clear that there's some sort of visual kind of mathematical pattern to these lines. As I move to the left, they're getting increasingly closer and closer together. And Lyman does something what a lot of people what I would say, not lazy people, but just what you first would do. You see a pattern of wavelengths or numbers to come up with a formula that predicts those numbers. And so Lyman comes up with a formula. Lyman says that the wavelength of one of these lines is equal to a constant, which I'll define in a second, called R sub h. It's a constant, times 1 minus 1 over n squared, where n is a number at least 2. It's an integer at least 2. All right, and what he shows is that if we assign each of these lines an index n, the first one is 2. This one is 3, 4, 5, and so on. This fits perfectly. Well, it fits the R squared equals 0.99, roughly, greater than 0.99. And he measures that R sub h, this constant, in modern units is 109,680 wave numbers. So he shows that this fits perfectly, and it gives you this number. Pure numerology. What I mean on numerology is that to Lyman or to anybody at the time, this RH number doesn't have any physical meaning. We'll see that it does have physical. None of this, or what does n mean? None of this is just, he just made a function up and wanted to fit the data to a function. Okay, really numerology. No scientific intuition other than statistics. But there's a trick. Something interesting happens. By the way, I don't think Angie is here. I wish Angie were here. She'd like to comment. Lyman, in particular, the Harvard astronomers, is a really interesting story. I highly recommend reading if you're interested in feminist scientific history. The Harvard Observatory is one of the greatest observatories in the early 19th century. It wasn't until Hubble, Edwin Hubble in Arizona, kind of took over the reins of astronomy. Harvard used to be the #1 place to do astronomy in America. And it was run by a bunch of astronomers. And of course, the astronomy community was all men. But all of this work, all the astronomical work itself was done by a group of women. I can't remember the name, what they were called. I think they were called the Harvard Computers, who did all the calculations, all the photographic development, all the plate analysis, all the astronomy, all the hard work was done by a group of women for about 30 years. One of the most successful groups of data analysts in history, completely a bunch of contracted women working for minimum wage, with no power whatsoever, being run by a bunch of male astronomers who did none of the actual work themselves. So this is actually a great success of feminine ingenuity, was the synthesis of all of this spectroscopic data from astronomical observations to come up with these kinds of results. It was really a women-powered project. But the thing that made Lyman's result interesting is to go back into Fraunhofer's visible spectrum and look for hydrogen in the visible. This is in the UV. We can't see these lines 100 nanometers. It's well past the blue. So there's another guy named Balmer. I don't remember where Balmer is from off the top of my head. You'll have to forgive me. And Balmer studied the visible emission spectrum of hydrogen, which we now call the Balmer series. So here's a visible picture of that spectrum. This is called the Balmer series. Okay, and what Balmer shows, very pretty. What Balmer shows is that this can be fit to another date, to a very, very similar function, but slightly different. Instead of 1 minus 1 over n squared, it's 1/4 minus 1 over n squared. And n doesn't start at 2, but it starts at 3. So this is the 3 line, this is the 4 line, this is the 5 line, the 6 line, and so on and so forth. And then you go fit RH here, and the value is exactly the same that you get for, what did I write it down? Sorry, let me get it over here. The value is exactly the same that you see for the Lyman series. Same. Right, but the only difference is that there's a difference in the formula. The ends are slightly different. You have this factor of 1/4 instead of 1. But the data fits exactly the same. It fits beautifully. R squared. Beautiful data. Same result. Balmer again has no intuition on what's going on. Right? But Balmer shows that Lyman's result is exactly the same as his. It's just another progression of lines in hydrogen that follow the same pattern, but are in some sense shifted by some amount into the visible. Right? So same behavior as the Lyman series. All right, well, that's really cool. So in fact, you can go into the infrared, go a little further along your wavelength, you see another series of lines that fit to the same formula, but instead of 1/4, it's 1/9, and n starts at 4. Okay, so there's another pattern along the wavelength in the infrared called the Paschen series that has the same properties as all the other series. They're just, the formula is just very slightly different, and they're at a longer wavelength. So that's cool. The physicists and the astronomers are very happy about this. They, in some sense, have come up with a magical formula that allows them to predict where every single line of hydrogen is. That's awesome, because that really helps you with astronomy. Now the astronomers know exactly where to point in terms of wavelengths, where to point their telescope at to see hydrogen, right? You pick maybe this red one or the Lyman alpha line, right? You have all these really, really nice isolated lines that allow us to look at hydrogen alone. It's really, really powerful. It enables a huge revolution in astronomy, right? Astronomy stops becoming about taking pictures with visible light and starts taking pictures with spectrographs, right? We take pictures of hydrogen now. Really, really powerful tool. And so, of course, astronomers and chemists, they want to do the same thing, but for every other atom, right? We say, well, we've got it working for hydrogen. Let's go do it for helium. Let's go do it for sodium. Let's go do it for oxygen. We'll do it for carbon, right? Maybe this formula works for all the atoms. It's completely universal, right? Maybe this isn't just a hydrogen thing. Maybe we've solved all of atomic emission spectra. The problem is it doesn't solve any of the other atoms, because when you go take a spectrum of all the other atoms, I have a nice picture here for you. Right, here's sodium, nitrogen, hydrogen, and oxygen in the absorption and emission bands. And you can see they all look very, very different. They all kind of look like they have some sort of pattern. Nitrogen looks a lot funkier than sodium, or oxygen also looks kind of weird. They don't look quite like the same collapsing patterns that we saw for hydrogen. But you can kind of see that they do look kind of similar, right? Nitrogen and hydrogen do have some similarities. Nitrogen has more lines. Sodium kind of has a clump at 450. Things are collapsing, but it doesn't look really all the same. And of course, none of these, other than hydrogen, fit to Lyman's formula. In fact, you have to come up with a new formula. There's one that fits for nitrogen. There's one that fits for sodium. There's one that fits for oxygen. There's one that fits for hydrogen. You can come up with a formula that allows you to predict these lines, but each one has a different constant. It's a different formula. So none of them have anything in common with each other, other than that they have patterns that can be fit. But as far as we can tell, they're all fit separately. So whatever I learn about hydrogen, I can't really apply to oxygen. That should bother you as chemists, because that would imply that in some sense all the atoms are different, which they are. I mean, they are all different from each other, but they're all made up of the same stuff. They all work under the same rules. They all have angular momenta, radial, they have interactions, they're electrostatic. They all kind of work under the same thing. So you would imagine that these are all formed under the same principles. same physics determines these spectra. And the distinction is that you have different atoms, different number of electrons and protons, and that causes these changes. Because we have a periodic table, we would imagine that these things are all related because every other chemical property is related. So there must be some sort of theoretical connective tissue that bridges all of these together. Maybe doesn't give us one really simple formula, but at least gives us a common workflow to determine the formula, right? There is some pattern, and the pattern depends on the atom, but there's some master theory that predicts that pattern. Right? Well, in 1910s, they didn't have that luxury, right? They just had these spectra, and no way to bridge the gaps between the two. Well, that's where quantum mechanics comes in. Right? All of this was done pre-quantum mechanics, but every single one of these results, as I'm sure you're well aware, are quantum mechanical. The only thing that gives you absorption peaks and emission peaks are quantum mechanical objects. You know that it basically has quantized energy levels. So there must be some underlying master theory that allows me to get any of and all of these patterns. Right? It's a key for us to understand that those master rules. Right? And that was the kind of missing piece that they were having, was the quantum mechanical part that connects all of these together. So what we're going to look at is hydrogen in particular and understand hydrogen spectrum and its emissions. And then what we'll do for the following week is to take our idea of hydrogen and then use that what's the word I'm looking for? That periodic table type of philosophy where we know everything is related, right? You can think hydrogen is probably pretty similar to all the other atoms that have one unpaired electron in their valence shell. And helium is probably pretty similar to neon and argon because they have all their valence shells filled. And the halogens are probably all similar because they are all filled except for one. And then you might even think, well, hydrogen and fluorine both have one unpaired electron. Maybe they're similar too. Right? And we'll see that consistency of how many electrons you have in your valence shell do determine these patterns. And we'll see that the atoms that lie along sodium's period or the ones that lie along nitrogen's period tend to have very similar patterns to each other. And it has to do with how many electrons you have in your valence shell. So it's good to start with just one electron, see how one electron works, and then we can start to think about multiple electrons. Again, even at this time, they didn't know what an electron was. That's the important thing. Is Millikan or J.J. Thomson discovers the electron in the 1900s. Didn't really measure the charge until the 1910s. It's only very recently that Ernest Rutherford discovered that there was a nucleus in the atom, right? All of these things are developing independently from each other all at the same time. So they are kind of all pulling from each other, but not really. There's no like universal connective linkage. That's what quantum mechanics is, that connective linkage between all of these observations that were being made at the same time. So what's the correct answer? All right, so for hydrogen, remember that in hydrogen, we have wave functions. We can write them down. We looked at them last class. All right, so we can think about the Hamiltonian for hydrogen being applied to our wave functions that are labeled N, L, and M, right? That we wrote down before. And we know that when we do this, we're going to get an energy back, the energy of the hydrogen atom, say E sub n, times the wave function. Okay, we could go evaluate this. We've already written down the wave functions and Hamiltonian. We could go do that math if we wanted. Factor out psi and get E. But I'll just write down the answer. Right, once you do this math, once you find out is that E sub n, the energy only depends on N. It does not depend on L. We'll have to think about that for a second. Is equal to minus E squared over 8 pi squared epsilon naught A naught. We talked about A naught last class, right? 0.5 angstroms. Did we do that last class? Yeah, okay, good. A naught times 1 over n squared. Okay. So the energies of hydrogen go as 1 over n squared. Kind of a funny formula. We'll have to look at that a little more carefully. Let's see what if this gets us the answers that we saw Balmer and Lyman do. Can we reproduce the same result as them? Right. So for Lyman, remember that the n number that we use starts at 2. Right. And if we go back to our discussion about the wave functions, remember n starts at 1. So here n can be 1, 2, ... Right? Lyman fits things starting at n equals 2. So there's an n equals 1 state that he's not considering, but remember we're doing spectroscopy. So Lyman doesn't know anything about energy levels. He doesn't know anything about this. He doesn't know that his n corresponds to an energy level. No concept of that. But what we do know is that he's looking at absorptions. And his absorptions start at some upper level n equals 2. So the only thing that all these levels could be coming from is n equals 1. They all have n equals 1. So Lyman's starts at n prime equals 2. That's the upper level. Upper. And his lower level, n double prime, is equal to 1, his lower level. All right, so the Lyman series are absorptions originating from the 1s orbital. Ground state hydrogen. So let's see if we get the right formula. So Lyman is calculating delta E, so delta E Lyman. That's going to be the energy of the n prime state, whatever that number is, that's his Lyman lines, minus the energy of the ground state, which is n equals 1. Okay. That's going to be equal to minus E squared over 8 pi squared epsilon naught A naught times 1 over n prime minus 1 over 1. Or sorry, n prime squared. Times minus 1 over 1. I can distribute the minus sign. E squared 8 pi squared epsilon naught A naught 1 minus 1 over n prime squared. Well, there's that 1 minus 1 over n squared that Lyman had. All right. So now what we have to do is figure out what this value is. And if it's the same value that Lyman had, then Lyman had the right answer. All right. So I think I have you kind of calculate this in a homework in some way. And what you find is that when you evaluate this number in wave numbers, it's 109,678 wave numbers times 1 minus 1 over n squared. This is exactly the same as Lyman and Balmer. So Lyman got the right answer. Lyman just came up with this 1 minus 1 over n squared relationship and just fit it to like a slope. Linear regression, and the slope was this constant, this 109,000 constant. You got the slope for it, and then you go do the actual quantum mechanics, and you get a bunch of constants out, and it's exactly the same value. But Lyman got the right answer. He got it for the wrong reasons. In fact, he got it for no reasons at all. He just guessed. But he gets exactly the correct answer. All right, so Lyman's lines are ones that are moving or originating from the 1s orbital. So what about Balmer? Well, remember that the only difference between Balmer and Lyman was that the first value of n goes up by 1, and now you have a 1/4 here. How do we get a 1/4 from this equation? Well, for n equals 2. So what that means is that the Balmer series are the absorption lines of hydrogen originating from the N equals 2 state. Maybe 2s, maybe 2p, I don't know. It's originating from the 2 orbitals. So the Balmer series is n prime greater than or equal to 3, and our lower level is 2. And then E Balmer is going to be the Rydberg constant times 1 over 2 squared, which is 4, minus 1 over n prime squared. Okay, exactly what Balmer got. So they were just, in some sense, they got lucky with hydrogen. Balmer and Lyman's approach doesn't work for any of the other atoms. You can come up with a formula to predict the helium lines, but it doesn't look so clean. Just put it back. Doesn't look so. But it just happens to work just right for hydrogen. And that was just enough for us to get started. Right. So just enough of a foothold to start the theory. Now we kind of have the Balmer and Lyman had an appreciation for the energy level structure of hydrogen. We just needed the physics to finally agree with the observations. Okay. So one thing I want to spend a moment on is this formula for energy for hydrogen. First of all, it's not dependent on L. What that means is that the 2s, the 2p, the 2s and the 2p orbitals have the same energy. The 3s, the 3p, and the 3d all have this. All the n equals 4 orbitals have the same energy. That seems odd, because if you guys remember, when you guys fill electrons, when you have a bigger atom and you're filling orbitals with electrons, how do we fill? We fill 1s, then 2s, then 2p, then 3s, then 3d, and then I think it's 4s and 3p, anyway, regardless. But you do them in sequence, right? Which means that the 1s is more stable than the 2s, which is more stable than the 2p, which is more stable than the 3s. Meaning that all of those orbitals should have different energies. But what hydrogen tells us is that in hydrogen, all the n level, for all fixed n, they're all the same energy. What's the difference? Well, in hydrogen, there's only one electron. When you only have one electron, all the orbitals were given intergenerate. When you bring in another electron, which is when you need to start thinking about filling orbitals, right? You have multiple electrons. The electrons begin to repel each other. And that repulsion causes the energy levels between the S's and the P's and the D's to split. So in helium, and every atom has helium, the 2s and the 2p and the 2e, they depend on L. And the energy for helium will have an L dependence in it, because the p orbitals are different than the s orbitals. But in hydrogen, we don't have to worry about any of that, because there's only one electron. It's not interacting with anything other than the proton. And so all the n levels are degenerate in hydrogen. Right? They become not degenerate in helium. But you might notice that what this means is that all the energies are negative. There's a negative sign there. That constant is positive, it's 109,000. And 1 over n squared, of course, is always positive. So these energies are negative. All right, so let's try to understand what these are telling us, what the scale of energy scale really is. I think it's kind of a useful way to think about this. So we have a very simple formula, which is that the energy of hydrogen is 109,678 wave numbers divided by n squared. I don't think I've introduced this unit yet, but another unit that we can use is electron volts. I'll introduce this in a few classes, so we can write that as well. Minus 13.6 eV. So what does this spectrum look like? Well, there's going to be some energy E equals 0. Right, this needs to be energy up here, sorry. All right, so we have some energy E equals 0. Okay, and let's go ahead and plot in our levels. All right, so E sub 1 is going to be at minus 13.6 on this scale. Right, this is the 1s orbital. Right? Where's the next? The n equals 2 are going to be at 13.6 divided by 4. So it's minus 3.4. There's a 2s orbital, right? And then there's 3 2p's. They're all at the same energy. And then there's the n equals 3, which is going to be at 13.6 divided by 9. Is that 1.5? Right? There's a 3s orbital. There are 3 p's. And there are 5 3ds. Right? And then the next one's going to be at 13.6 over 25, which is at 0.5. This is the 4, right? And you can imagine what happens is that as n increases, this number is getting closer and closer to 0, right? But it never reaches 0. The only n that gives us 0 energy is infinity. So the limit as n goes to infinity of E sub n is 0. So this is the infinite limit. So the question is what's past that limit? Right? What if I get the energy, right? What if I put 13.7 EV into this system? Or 14? I put more energy than the binding energy of that electron, right? So what if I put myself above that? Right? What have I done? So there's this region up here of positive energy. What does that mean? Well, remember that in hydrogen, the electron is attracted to the proton. The dominating force is the potential energy of the electrostatic attraction, which is attractive, right? Attractive between plus and minus, which is a negative potential. So having a negative energy means that there is an attractive potential to the electron, meaning that it takes positive amounts of energy to remove it. So what that means is that if we're in the 1s orbital, which has minus 13.6 eV of energy, that means it takes 13.6 eV of energy to remove the electron. Not surprisingly, if we were in 2s, it would take 3.4 eV to remove the electron. So the state that's above the 0 limit and the dashed is the ionized state of hydrogen. It's the electron is now gone. Up here we have just proton and electron. So this value, E equals 0, is the ionization limit of hydrogen. So let's think a little bit about what Lyman observed in his spectrum. Remember, Lyman is seeing lines that are originating from n equals 1. So here's the Lyman alpha. Right, from 1 to 2. There's the Lyman beta. The Lyman gamma. Right, and as you can see, as I start to climb up and up and up, the gaps between each individual level are getting closer and closer together. So what I should see is that the absorption lines should start getting closer and closer together. Let's go back to the picture. Right, so here's my first line. That's one at between the two closest states, but stay closest to n equals 1. It's going to be the closest, lowest energy or longest wavelength, line alpha line. Right, and as you start to climb the limit, your absorptions start to collapse towards this limit of 91.2 angstroms. What is that limit? Well, that limit is the ionization limit. If you go convert this number right here, 902 angstroms, into energy, this is 13.6 EV. So what you're seeing are the lines of hydrogen collapsing towards that ionization limit. They never quite reach there because you need to infinitely excite the electron to get there, right? Or give it more and kick it out. But your absorptions, your bound absorptions, where the electron is still stuck to the proton, they get closer and closer and closer together to that limit. So Lyman indirectly, well, direct, he didn't know it, measured the ionization energy of hydrogen without even knowing. So Lyman determines with very high precision, this is the enthalpy of H going to H plus plus an electron. And he just happened to measure it, and he had one of the most accurate measurements of that value by measuring the limiting case of that collapsing progression, which is exactly the ionization energy of hydrogen. Right? This is how we measure ionization energies in modern times. Is we use spectroscopy. We use a light source to kick the electron off because we can measure the wavelength of the emitted photon or the absorbed photon very, very precisely. And Lyman didn't have an appreciation for that, but he did it in 1906. He didn't even need to use a multimeter, some voltage meter or a current meter. He used spectroscopy to measure that. Okay, so when we talk about hydrogen, when we talk about atomic energy levels, we often reference them with negative energies because the definition is that zero energy is the ionization level. This is a very common way for us to do this. Right? It's just a relative scale of energy. We could write it any way we wanted. We could set this to be 0 and then the ionization limit to be plus 13.6. That's totally fine too. Nothing wrong. Okay. Cool. So that's our hydrogen spectrum, as far as we know. Now, as we move through the 20s, the teens into the 20s, Lyman and Balmer, we get all the hydrogen information done. Bohr does his work, the Solvay conference happens. People are starting to learn quantum mechanics. At the same time, optical technology is improving. Diffraction gratings are getting more sensitive. We're able to split wavelengths out even more finely. We can measure things more and more finely. We haven't developed lasers yet to do things really, really accurately. But we're getting better light sources in the lab, better telescopes, and resolve lines and resolve splittings much more finely than we did 20 years before. So in the 1920s, people went back to study the hydrogen line at higher resolution. All right, we got a new instrument. Let's go test it on my new end. Let's go use a system we know really, really well as a reference, which is hydrogen. Let's go test our new instrument with it, right? Our new spectrometer. Let's see let's do the best measurement of hydrogen anyone's ever done, right? Every spectroscopist does this. We get a new piece of toy and we put something really trivial in there just to see how an easy project just to impress ourselves. And so new visible spectrometers came out with high resolution, diffraction gratings, and the visible. We're starting to look at the Balmer series of hydrogen in the 1920s. And so in 1921, a very interesting report was released on the Balmer alpha line, which is the N equals 2 to 3 transition of hydrogen, right, which is in the red, hence the color of my text. And what the astronomers find, or rather the spectroscopists find, is that there's not one line there. It's not a single absorption, but it's a very, very finely split doublet. Well, instead of there just being one line, here's a picture from the plot from the 1921 paper of this doublet in the Balmer alpha line. And here's a photographic plate of the multiplet from an emission spectrum hydrogen. All right. So if we go back and look at our energy level diagram for where the Balmer alpha line is, that's this line here. It's coming from 2 and ending somewhere up in 3. All right. Notice that all the 2 levels are at the same energy, and all the 3 levels are at the same energy. So no matter what my initial state is or my final state is, whether I start in the P's or the S's or end up in the D's or the P's or F's, right, doesn't matter. I get the same absorption frequency. I should only see one line, right? Because everything's at the same energy. But when I go look at it with fine enough resolution, it's a doublet. There's two states there. So that means that, in fact, we're missing something in the hydrogen spectrum. Some things that we think are equal energy are not actually equal. There are a couple of different possibilities of what could cause this. All right, so what could cause this? Explanations. Well, one is, what we thought was this, is that there's just one level for each one. Right? This is what we originally thought. This is the original theory. Right? And when this is no good, right? Because this predicts a singlet. Right? So that means that one or two of the levels have to get doubled. There has to be a split. An additional, at least one additional state somewhere. And there's two possibilities. Well, there's a couple of possibilities. One is that we have two different states in the same final state. Call this 2' and 2. Right? And we have two lines of slightly different wavelength. That's a possibility. Another one is the opposite, of course, where you have one ground state and a split upper state. You have this. Or we could have both of them split. But each set goes to one of the other of the pair and not the other one. So there's no cross. So we can maybe 2' goes to 3' and 2 goes to 3, like that. Right? We have some options for what could explain this. But nothing in our theory for hydrogen predicts that any of our upper states or lower states should split. They're all degenerate. So we've missed something in our theory. Right? There's something else going on in hydrogen that we haven't accounted for. What could be causing the energy levels to split? Right? So in some sense, we've accounted for all of the forces in hydrogen. The electrostatic force, the angular momentum, and the spin. But what we haven't considered is if those forces interact with each other. We've added them all separately to each other, right? We've treated spin and angular momentum and the radial energies as separate quantities that are just additive. But what if one affects the other? What if the angular momentum affects the spin, or the spin affects the angular momentum, orbital angle? What if there's some coupling between those motions? The way to think about it is like this, is to think about, well, I'll give you an example in a second. Right? So let me try to describe this, right? So what if there's some interaction between the forces? One modifies the other. And that turns out to be the right way to think about this. That what we have are not three independent forces, spin, orbital angular momentum, and radial, the electrostatic force, but we have some sort of interaction between two of the forces. One of them existing affects the results of the other. Kind of an interesting concept. Let me show you a physical explanation of this. So the result of this is what's called, is due to the interaction of the orbit of the electron with the spin of the electron. So it's a concept that we call spin orbit coupling. I'll even show you an example of spin orbit coupling, like physically, at the end of class. It's a real thing. So let's think about the angular momenta in our electron or in our atom. So we have a proton here, right? And we have an electron at some distance. And the electron is going, let me do it like this instead. I want to draw kind of at an angle. So we have some orbit of an electron. Right? I'll have the electron go counterclockwise. Right? which imparts some sort of angular momentum. So there's a net orbital angular momentum in this direction. Right? The electron is orbiting. Right? It might have L equals 0, it might be L equals 1, L equals 2, whatever. Some amount of angular momentum. What's happening at the same time? Well, the electron also has its own angular momentum, its internal angular momentum, which is its spin. And so what you can think of is that the electron kind of looks like it's orbiting around its own axis, right, with some spin angular momentum. And if the spin's in that direction, then it would also be precessing counterclockwise around its own axis. Right? This is kind of like the Earth, right? You think about the proton as the sun and the electron as the Earth. We have orbital angular momentum of the Earth, which gives us our year. And then the sun, the Earth is also rotating on its own axis, which gives us a day. So the spin angular momentum is kind of like the rotation of the Earth. The orbital angular momentum is the rotation around the sun. Okay? And the slowing down, let me think about it. So I think our year is getting slower and our day is getting faster. Because we're angular momentum conserved. So as one angular momentum decreases, the other one increases. So as we slow down around the sun, we actually spin up ourselves because of conservation. So these two angular momentum in orbital mechanics are coupled to each other. The angular momentum of the Earth is affected by the angular momentum around the sun and vice versa. Now the Earth's angular momentum doesn't really affect the sun at all, but the other way certainly does. This is a really dramatic case with the moon, right? This is tides, right? We get tidal locking, which is the extreme example of where orbital angular momentum couples to internal angular momentum, where you get tidally locked things and things all rotating, right? Like the moon does, right? The moon no longer rotates on its axis relative to us because it's tidally locked to us. That's a really, really, really strong coupling between orbital angular momentum and spin. So this works, but you can imagine there's a different way to draw this, because I could also have the electron orbiting counterclockwise around the proton. So I have L in the up direction. But I could have spin in a clockwise direction, right? I could have the electron moving in the opposite direction. The opposite direction, which would mean that its spin axis, its spin vector, is pointing in the opposite direction of the angular momentum. Okay, so we have in some sense, we have two different options of how the net angular momentum system is working. One is that we can have the angular momentum of the spin be coupled and concerted with the angular momentum of the orbit, or we can have them working against each other. So what we're going to do now is we're going to combine those two angular momentum together. Think about the total angular momentum. So what we're going to do is define the total angular momentum. Right? Which we always call J. And that's going to be L plus S. We're just going to add the two vectors together and define a new angular momentum vector, J. And J satisfies the same rules that L and S do. Right? We have the J squared operator acting on psi, giving us H bar squared J plus 1 times psi. And we have the Z component acting on psi, giving us H bar times M sub J, the Z component of the angular momentum, the total angular momentum on the Z axis psi. Right, so it works exactly the same way. But now our angular momentum is a sum of two angular. So what we should do is we should define a state for L and S and look at what J looks like and see how it changes. And let's set up these two problems and calculate J and see if they're different. If somehow these two arrangements of the angular momentum lead to different states. Right, so let's do an example. Let's take L equals 1, so that's a P state, right? Which means that M sub L is either 0 or plus or minus 1. Right? And let's set S to be 1/2, meaning an electron. And that means that the spin can either be pointing up or down with components plus or minus 1/2. So there's a P state. We're just going to define a P electron. Doesn't matter if it's in 2 or 3 or 4, it doesn't matter. And then what I'm going to do is draw a little axis system, right, where I can draw my little vectors. Right? I'm going to put my electron at the center. This is my electron. Right? And I'm going to draw my vectors for it. Right, so let's pick the first one. Let's do M sub L equals 0. So this is the z-axis. So this is L pointing along the x-axis or the y-axis. It doesn't really matter. Okay. And then we're going to add a spin to it. The angular momentum is pointing in this direction. We're going to add a spin, and let's pick one or the other, right? We either have spin pointing up, that's M sub S equals plus 1/2, or M sub S equals minus 1/2 pointing down. Each of these one of these is a clockwise and one's a counterclockwise. That's the only difference between the two. Just the holicity of the rotation. So I could choose this one, right? This would be my S vector, right? And this is M sub S equals plus 1/2. Right, but I could also add to it this vector, which is M sub S equals minus 1/2. I could pick either one. And then I'm going to form J. How do I form J? I just add the two vectors together. I've already drawn them tip to tail, so we just draw the resultant vector tip to tail. And so I have one J value here. Right, so one of my J vectors is here. We'll call that J plus. And there's an equivalent vector down here, which is the sum of the minus component, J minus. Okay, so now I have these two new vectors that are pointing in different directions. Right, what are the values of J and J sub Z, the two components that I can measure? Well, J is L plus S, which is 1 plus 1/2, which is 3/2. And M sub J, well, we have two different components, right? We can either add 1/2 to 0 or we can subtract 1/2 to 0. Right? So I either have 1/2 or minus 1/2. So what I've done now is I've taken two angular momenta and added them. And I've created two new J states, both of which have J of 3/2. Total angular momentum is now 3/2. And now there's components that are either 1/2 or minus 1. So this creates a doublet of 3/2, 1/2, and 3/2 minus 1/2. But remember, S can also be pointing in an opposite direction too. It doesn't have to be pointing straight out. It can be pointing up, but pointing backwards relative to L as well. It doesn't matter which direction we're going. So there's an equivalent way to draw this. I'll just kind of roughly draw it for you. Where L is in this direction, and then S is pointing in this direction instead. Right? That's perfectly allowed. Right, because we don't really have any definition for S on the XY plane. We only know the Z direction. We know it's pointing up, but we don't really know if it's pointing opposite L or with L. So there's another option, which is adding L to the backwards S. Right? And then we form two new J vectors. And what are these values? Well, here J is equal to L minus S, which is 1 minus 1/2, which is a half. And M sub J is 1/2 and minus 1/2, either one. So now I've created new angular minimum states, 1/2, 1/2, and 1/2 minus 1/2. Right, if I took M sub L equals 1, where now L is also pointing up or down, then I'm also going to get M sub J equals 3/2 as well. But the important thing now is I'm taking a state of a given L equals 1, and by adding spin to it, I've created two new states. I've created a lot of states, a bunch of different M sub J's. But I've created two particular new J states, two new angular minimum states, one that's 3/2 and one that's 1/2. So by adding a spin to an electron, by adding the electron spin to the orbital spin of the atom or the electron, I create two new states of different angular momentum. One's faster than expected, 3/2, and one's slower than expected, 1/2. Right? I get that J here is L plus 1/2. And here I get J is equal to L minus 1/2. So these are two different states of different angular momentum. These have different energies. And the problem set I'm going to have you kind of explore how much energy this split is. But the point is that when I add two angular momentum together, I get new angular momentum. And it causes me to have a splitting now of two different states, a 3/2 state and a 1/2 state that have different energies. One of the states corresponds to a constructive addition of the two angular momentum, where the two angular momentum are working together for the electron to spin faster than expected. And then there's a combination of them that slows and retards the electron down. It's not orbiting as fast. In some sense, the spin is adding drag to the orbit. So it's not orbiting as fast as you would expect. That's going to have a different energy, different kinetic energy, different potential, therefore different energy. So spin-orbit coupling causes the levels to split. So let's draw that. What does that look like in terms of energy levels? Well, in general, what we can say is that there's a simple rule when adding two angular minima. L1 and L2, such that J, the total angular momentum, is L1 plus L2. Right? L can be spin as well, any sort of angular momentum, with numbers L1 and L2 respectively. J has quantum numbers. J, we'll call them J, that satisfy the following formula. That J can take any value between L1 minus L2, L1 minus L2 plus 1, L1 plus L2 minus 1, and L1 plus L2. Okay, so it takes, J can be any value between the sum of the two angular momentum and the difference, absolute value. So we can just quickly calculate for our L equals 1 system, right? If L equals 1, if L1 is 1 and S1 is 1/2, then J can be either L1 plus S1, which is 3/2, and it can be L1 plus S1 minus 1, which is 1/2, which is equal to the absolute value of L1 minus S1. So there's only two allowed values for the P state. So we call that the P doublet. What about for L equals 2, the D states? Well, J can be 2 plus, it could be 5 halves, it can be 3 halves, and it can be 1 half. It's a triplet. So the D forms a triplet. And so on and so forth. These are called spin orbit states. Right? Every atom has a spin orbit state. Every atom is spin orbit coupled. And in fact, as you'll see in the homework, as the atom gets bigger and has more and more electrons, more positive charge in it, the spin orbit becomes even more important. In some sense, in hydrogen, it's minimum. By the time you get to the heavy atoms, the metals, mercury, for instance, the electrons are orbiting so fast, they're relativistic, that the spin orbit coupling is so strong that it fundamentally changes the energy level structure of the system. It's not small splitting, it moves the energy levels. And in fact, there was a really fascinating paper about 20 years ago that proves the reason why mercury is a liquid and not a solid at room temperature is because of spin orbit coupling. Spin orbit coupling changes the energy levels so much in solid mercury that solid mercury becomes unstable at room temperature relative to liquid. So it's a really, really important concept. In the last 5 minutes, I want to show you an example. Unfortunately, for the people in Zoom, they won't be able to see this. An example of spin orbit coupling in real life. All right, I'll give you some examples as we go through. Magnetism is a big one. But glow-in-the-dark objects are a consequence of spin orbit coupling. Let me show you an interesting example. I have a demonstration for you. Glow-in-the-dark. Here I got a watch. My watch here, I've got a bunch of, on my indices, I have these little pads that are filled with this, I don't know what you call this, powder. It's kind of a gelatin powder. It forms a solid and it has a binder of this glow-in-the-dark material called lube. So these little pads have something called this luminous material. In watches is an organic salt of heavy atoms, such as europium. And other actinides. Right? These are atoms with a lot of electrons. A lot of electrons. They have very, very strong spin orbit coupling. Very strong spin orbit coupling. All right. So let me explain to you how glow-in-the-dark works. The idea is that you have 3 energy levels in a glow-in-the-dark material. The idea is that you have a ground state. Sorry, ground state. Okay. And we can assign for the electrons in that ground state some net angular momentum of their orbital angular momentum. Let's just say it's in an S state, right? Let's just say it's L equals 0. Okay. What I have here is a UVA flashlight, right? It's a flashlight that emits at 365 nanometers at UVA. You guys can see it. It's not really anything. If I put it in your eyes, it hurts. You can kind of see can you guys see it? I want you to look at my pads on this as I shine it. Glow bright right? Glow bright blue. 3 inches in. So the europium, the dyes, or the lume object, which is this europium salt, an organic ligand, absorbs UVA very strongly. Okay, so there's an excited state. And let's say that the net spin is 0, right? Because it's a singlet. Right, so all the electrons are paired. Okay, and so you excite the state with UVA. This is what did I say the wavelength was? 355. The UVA light, right? 355 nanometers. This is the blue. Right? And you create an excited state. And what do we see? When I excite it, it emits immediately. Right? It looks reflective, but it's not really reflective. It's actually emissive. it's absorbing my UVA photons and immediately re-emitting them through fluorescence. So we have a very rapid fluorescence of our lume, right? And so you get this blue emission, rapid blue fluorescence, right? And as you can see, it's glowing really quickly, and then the moment I turn the light off, it stops. It's still glowing. It's glowing dark, but it's glowing. The kind of reflectivity, the bright glowing, disappears immediately when I pull the light away. Right? Because the fluorescence is stopped. It's very rapid. It quenches very rapidly. But as you can see, when I let go, there's still some light being emitted. And notice the color of the light, right? This is bright blue, very clearly blue, violet or indigo, as you would say. This is more of a green color. What's happening? Well, it turns out there's an intermediate state in the system that's slightly lower in energy. Over here. And in this state, let's just say the excited state is L equals 1 and S equals 0. What will happen is the angular minimum and the spin of the electrons in the europium couple very, very strongly. And what you'll get in this state, this intermediate state, let's say is L equals 0, but it's S equals 1. What you find is that with light, S cannot change. S can't change. So with light, this is forbidden. Does not allow. But if you couple the angular minimum to the spin, you can transfer the angular minimum of the electron into the spin of the electron and get it to flip through spin orbit crossing or spin orbit coupling. So with SOC, spin orbit coupling, delta S is not equal to 0. So with spin orbit coupling, I can move molecules from the excited UVA state into this intermediate state. Okay, it's slightly lower in energy. It emits some infrared light, or it's radiationless, actually. It's radiationless. Transfers over to the intermediate state, not through rate emission, but through a spin transfer, through energy transfer of angular minimum. There's no photon that's being emitted. And then what happens is that the molecules get trapped in this intermediate state. This state right here, this is forbidden, or very, very, very slow. Because this state is S equals 0 and L equals 0, and delta E is very, very big. It turns out that, so the two states of the intermediate state and excited state, they're close in energy. So spin orbit coupling is fairly efficient. And so they can funnel molecules over into the intermediate state. But in order to get molecules from the intermediate state down to the ground state, I need to flip the spin again. I need to go to S equals 0. So I need to spin orbit coupling to kick in again. But the gap of energy between the two states, the ground state and intermediate, is so large that spin orbit coupling is very slow. So the molecules get trapped in the intermediate state, and then they trickle very, very slowly into the ground state. So I have a very, very fast excitation. Fast. I kind of have a slowish transfer, and then a very slow decay. And it's at longer, lower energy, which means longer wavelength, closer to the red. So what I'm doing here is I'm pumping molecules into the excited state. Most of them are fluorescing out, but I'm slowly driving the molecules over into the intermediate state where they get trapped. And then when I turn the fluorescence off and quench the main UVA route, I just see the trickle of the more green, more red, less blue, lower energy, longer wavelength photons that are slowly trickling from the intermediate state. The only reason why they end up in that state in the first place is because of spin orbit coupling of the europium atoms in the pigment, in the fluorescent dye or whatever it is. All right, so this is every glow-in-the-dark object goes through a process called phosphorescence, and phosphorescence is almost entirely due to spin orbit coupling of the chromophore in the thing that emits. Okay, so that's a good example of spin orbit coupling. Another place where this plays a role is in the photosystem and photosynthesis. Same idea. You're bringing in UV photons and you want to convert them into energy. You don't want to just excite something and then fluoresce it out immediately. You want to trap that energy and store it so that you can use it for metabolism. And so planet cells use spin orbit coupling to excite the system into an excited state, and then use spin orbit coupling to trap it into an intermediate state where it's long lived, and then can be used for other purposes. Okay, so that's